up, what up? Welcome to the fourth unit of AP Precalculus. Now, the fourth unit is not tested on the official AP Precalculus exam. So if you're watching this, you're not watching this to get yourself prepared for that fun day in May where you have to take the test. But maybe your teacher is going to teach this stuff to you, or maybe part of it to you. Maybe it is technically part of the curriculum. It's just not tested. So, rather than make the 4 videos that I always make with these and kind of like split them up into hour-long videos and then put them all together to make like this wonderful 4 or 5 hour extravaganza, I'm just going to make one video doing the whole thing, kind of going over the meat of Unit 4, and maybe it'll be like an hour and a half, 2 hours long. It all depends on how much fun I'm going to be having. But let's start out by talking about parametric equations, okay? Let me move my face because it's in the way. A parametric equation is basically, instead of giving like an x value and plugging in to get a y value, you're given a t value. And that independent variable t is plugged into both an x and a y equation to get you a coordinate. So as you can see right here, you have a t, and you pick some t values, which I'll do. So like -4, -3, -2, -1, 0, 1, 2, 3, 4. And what you do is you take those t values and you plug them into the x function to spit out an x. You plug them into the y function to spit out a y, and then you just get a bunch of coordinates that may not necessarily line up with the t's that you choose. It's just what you get. Okay, so that's what a parametric function or a parametric equation looks like. So x of t, or just x, is going to be t. So let me do that guy first, and then I'll do y of t. And the nice thing about this is whatever t is, x is also. Does that happen all the time? No. Does that happen with this problem? Yes, because that's the problem that I chose to do. So whatever t is, x is also. Hooray. Now, y requires a little bit of work. Okay, so y is going to equal 1/2 t squared. So whatever t I choose, I square it, I take half of it. So -4 squared is 16, half of that is 8, so y is 8. -3 squared is 9, so half of 9 is 4.5, so I'll actually write it out as a decimal because it's easier to graph. -2 squared is 4, half of that is 2. -1 squared is 1, half of that is a half, so I'll put 0.5. 0 squared is 0, half of that is 0. And then fun stuff happens. 1 squared is 1, and half of that is 0.5. So, a number that repeats. 2 squared is 4, so half of that is 2. Again. 9, half of that is 4.5. 8. We get the same numbers. So in this case, it looks very parabolic. You know why? Because it's a parabola. Let me choose green because I didn't use that yet. Actually, black. All right. Let me graph these points. When you graph parametric functions, I'm going to label each point by the t value that I used. I'm also going to go and label the direction that this is going in as t increases, because that's part of graphing parametric functions. So -4 is 8. And so let me graph the points first, and then I'll do what I say I'll do, or whatever, so I have different colors flowing through this graph. -3, 4.5, -2, 2, -1.5, 0, 0, and then it goes back up and repeats the same behavior like that. Okay, so let me graph this function best I can, which is never good because I'm awful at graphing using this pen, as those of you who watch my videos know. Those of you who don't watch my videos, you can see why I just said that I'm awful at graphing. Now, what I'm going to do is I'm going to label every point that I drew based off of the t that I used to make the x and the y value. So this was t equals -4. This was t equals -3. T equals -2. T equals -1. T equals 0. T equals 1. T equals 2. T equals 3. And t equals 4. I'm also going to draw arrows demonstrating the direction that I took as the t values increased. So let me get a black marker or a pen to do that. It went in this direction as t increased. So I'm just going to draw a couple arrows going in that direction. Okay? So a parabola, when written in parametric functions, kind of looks like a parabola as long as x equals t. It kind of makes life a little easier when things are simple like that. So let's pray that things are always going to be simple like that. No. My head is in the way. That's all right. For this guy, I have a sine and a cosine. Okay, so looking at this, I'm kind of thinking, all right, sine and cosine behaviors, nothing's going on inside the parentheses of sine and cosine, so period of 2 pi. Let's pick some t values that are convenient, like 0. Let's do every quarter of a pi, so pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and 5 pi over, no, 7 pi over 4. Sorry, I don't want to use 5 pi, 7 pi over 4. Silly me. Jumping the gun. All right. My x value is going to be 2 sine t. All right, so this one is going to be 2 sine 0. Sine 0 is 0, so 2 times 0 is 0. 2 sine pi over 4. Sine of pi over 4 is root 2 over 2. 2 times root 2 over 2 is just root 2. Okay, 2 times root 2 over 2, the 2's cancel out, it's just root 2. I don't have all the space to show that step, so I'm just explaining it a little bit better. 2 sine pi over 2. Sine pi over 2 is 1, so 2 times 1 is 2. 2 sine 3 pi over 4. Yes, 3 pi over 4. So sine of 3 pi over 4, sine is positive in the second quadrant, root 2 over 2 again. So we get 2 times root 2 over 2, which is just root 2 again. 2 times sine of pi is 0, so 2 times 0 is 0. 2 times sine of 5 pi over 4 is going to be 2 times negative root 2 over 2, so this is negative root 2. 2 times sine of 3 pi over 2 is sine of 3 pi over 2 is negative 1, so 2 times negative 1 is negative 2. And then 2 times sine of 7 pi, not 5, over 4 is going to be negative root 2 over 2, so 2 times negative root 2 over 2 is, again, negative root 2. Okay, so those are my x values. My y values, 4 cos t is going to be 4 cos 0. Cos 0 is 1, so 4 times 1 is 4. 4 cos pi over 4. Cos pi over 4 is root 2 over 2. So 4 times root 2 over 2, the 4 and the 2 cancel out to make 2 root 2. 4 cos pi over 2. Cos pi over 2 is 0, so 4 times 0 is 0. 4 cos 3 pi over 4 is going to be, it's an x value in the second quadrant, so it's negative. So negative root 2 over 2. 4 times negative root 2 over 2 is the same guy as that, but negative. 4 cos theta is going to be 4 times, not theta, pi is going to be 4 times negative 1, which is negative 4. 4 cos 5 pi over 4 is going to be the same as that. Negative root 2 over 2 times 4 is negative 2 root 2. 4 cos 3 pi over 2 is going to be 0 because it's that x value of that. And then 4 cos 7 pi over 4 is going to be positive root 2 over 2. So 4 times positive root 2 over 2 is 2 root 2. All right. So again, what I'm drawing out is the point 0, 4 in this order. The point 0, 4, and then the point negative 2, 2 root 2. So let's put those points down. 0, 4 is right here. Okay. Negative 2 root 2 or regular root 2 is like 1 point-ish. And then 2 times is going to be 3 point-ish. So you're looking at something that looks like this. So like 1 point-ish, 3 point-ish. So something that looks like that. And then 2, 0 lives right there. And then root 2, negative 2 root 2. So basically this guy, but down here. 0, negative 4. Negative root 2. So somewhere around here, negative 2 root 2 is somewhere down here. Negative 2, 0 is there. And then negative 2, negative 2, root 2 rather, 2 root 2 is going to be up here somewhere. So starting in this direction, I have myself an ellipse. Now, in parametric equations, when you have an equation where one of them is sine and the other one is cosine, and the numbers, the coefficients in front of your sine and cosine are different, that's the ellipse. If they were the same, you would have a circle. If one of these was negative, you would have a hyperbola. But that's not what we have here. By the way, I started here. I went in this direction clockwise just because of which one was sine and which one was cosine. And I'm going to label the fact that t was 0, t was pi over 4, t was pi over 2, t here was 3 pi over 4, t was pi, t was 5 pi over 4. Here for that point, t was 3 pi over 2. And last but not least, the one that I almost screwed up, 7 pi over 4. Parametric. Parametric, more like pair of equations. Oh. All right, let's move my face again. All right. A golf ball is struck and has an initial velocity of 220 feet per second and has a launch angle of pi over 4 radians. So guy hits a ball really fast, pew, pi over 4 radians. Write a pair of parametric equations to demonstrate the position of the golf ball with respect to time t. So the general equation, if you're dealing with feet, okay, the general equation is the x equation is going to be your initial velocity times cosine of the launch angle, all of that, whatever number that is, multiplied to t. The y equation is going to be negative 1/2 g, which is the gravity constant, which this is going to change depending on whether or not you have meters or feet. In this case, I'm using feet, so I'm going to use a specific number. If I was using meters, I would use a different number. Okay, t squared plus the initial velocity sine theta, sine the launch angle, times t, plus whatever height that you're shooting this ball from, which the height in this case is going to be 0, so life is going to be easy. Okay, now, you are my initial velocity. You are my launch angle. My height is 0 because I'm launching this off the ground. The g that I'm going to use is going to be 32. If this was meters, it would be 9.8. But since this is feet, we're going to be 32. But that's the only thing that's going to change if we were using meters versus feet. Okay, just the g right there. So x is going to equal my initial speed, 220, times cosine my initial launch angle, or my only launch angle, which is pi over 4, whatever number that is, times t. Okay, 220 cosine of pi over 4 is root 2 over 2, so times root 2 over 2t. The 220 over 2 turns into a nice 110, and so we've got 110 root 2t. That is my x function. So if I wanted to be really, really good at this, x of t, but it doesn't really matter. My y is going to be negative 1/2 of g, which is 32 t squared, plus my initial velocity, which is 220 sine pi over 4 times t plus 0. Okay, so y is going to equal negative 1/2 of 32, which is negative 16 t squared, plus 220 times sine of pi over 4, which is also root 2 over 2, times t. So we're going to multiply those together. That is a times, not a minus. And then plus 0, I don't need it. So we'll say finally y of t is going to equal negative 16 t squared, plus, again, the same thing that happened here happens here, 110 root 2 times t. So that's my x, that's my y, and that's my pair of parametric equations. And if I wanted to, I can plug t in to find where my ball is, height and length, at a specific time. Isn't that neat? Now when you're playing golf, you can tell this to your friends, who I'm sure will be super interested. All of you golfers out there. All right, so here's a pair of parametric equations. We have 3 parts to this. So part 1 is let's find the point on the xy plane when t is 3. So very similar to what we saw in that first example that we did, where you kind of pick a t and you use that t to find both your x and your y. So the t that we're picking is 3. So x of 3 is going to be 2 times 3, which is 6. Y of 3 is going to be 3 cubed, which is 27. So when graphed, when t equals 3, you get the xy coordinate 6, 27. Okay? Easy peasy lemon squeezy. Find the average rate of change on the interval 1, 3. Now, when you're dealing with parametric equations, the average rate of change formula is not the same as what we're used to. It's not f of b minus f of a over b minus a. In fact, what we do is we kind of use the old school version of the slope formula and use that. So if you are my interval 1, 3, I'll still label you A, I'll still label you B, and since the slope is the change in y over the change in x, let's find the change in y. So y of 3 minus y of 1 over x of 3 minus x of 1. Fortunately, I did this part already. Y of 3 is 27 minus y of 1 is going to be me plugging in 1. 1 cubed is 1. I can handle that. X of 3 I already did. It's 6. Minus x of 1 is going to be 2 times 1, which is 2. This becomes 26 over 4, which simplifies to 6.5. So that's my average rate of change over the interval 1, 3. Yeah. Don't know why I made that sound. My face is kind of in the way. So let me move my face. Determine the distance from the origin 0, 0 to the position of the rocket. This problem was originally about a rocket. I forgot to get rid of that part. So the position at t equals 2. The distance from the origin 0, 0 to the position at t equals 0. Whenever you're trying to find the distance from the origin, you are going to basically consider the fact that we are on a xy coordinate plane. T equals 0 is going to give me some point up there. I need to find from here to here. So why don't I use like my version of Pythagorean theorem? Why don't I try to find the x values, square that, find the y values, square that, and that'll equal what we'll call z squared or c squared or whatever you want to call it. Okay, so basically what we're trying to find is we're trying to find the big square root of x of t cubed plus squared, not cubed, plus y of t squared. So I need to find x of 2 squared plus y of 2 squared. So x of 2 is going to be 2 times 2. So 2 times 2 squared plus y of 2 is going to be 2 cubed squared. So that's going to be 4 squared is 16. 2 cubed is 8. 8 squared is 64. That's going to end up being the square root of 80. 80 is 5 times 16, so we can rip out a 4. And we're left with the square root of 5. What's the distance? What's the distance? And that's because we end up with a triangle that is it a nice triangle? A 4 and an 8? No. No, it's kind of like, it seems like it should be like one of those special 30, 60, 90s, but it's not. It's just, nicer numbers kind of gives us a nicer answer, which is what we have here. All right, so part 1 of Unit 4 is mostly parametric equations. And the general idea of parametric equations is instead of plugging in an x and getting a y, you plug in some random number to get an x and a y, and that kind of gives you weirder shapes. So maybe a parabola, maybe a circle, maybe a ellipse, maybe what looks to be 2 parabolas side to side. It all depends, but that leads us to this next guy, which is called conic sections. So this is part 2 of Unit 4, is dealing and graphing with conic sections. Now there's 4 types of conic sections. One of them we kind of saw twice when we did parametric equations. One's a parabola. I'm not going to spend too much time on a parabola because you guys have been graphing parabolas since Algebra 2, maybe even Algebra 1, probably Algebra 1. But the 3 other main conic sections that we're going to focus here is circles, and this is the general equation of a circle where the center of the circle is HK. Probably should have said that. In fact, the center for all of these is going to be HK. Okay, circle is just a regular circle. Ellipse, we graphed one of those, is going to be like the oval, so it could look like one of those ellipses. It could look like one of those ellipses. And then you have hyperbolas, which could be horizontal or vertical, depending on whether your negative is in front of the y or your negative is in front of the x. Okay, in all of these ellipse, hyperbola cases, ellipses and hyperbolas look exactly the same until you get to this part right here, where ellipses you add and hyperbolas you subtract, okay, one of the main functions, or one of the main fractions rather. So it all depends. By the way, hyperbolas look like those parabolas that I talked about like a minute ago. So that's one version of a hyperbola. That's another version of a hyperbola. It all depends on where your negative lives, and we'll get to that. Okay, we'll get to that. So let's start right off the bat by graphing a circle in that form. Now, if you have these memorized, they're very, very, very similar in nature. Circle is very easy to memorize. The equation of a circle is going to be x minus h squared plus y minus k squared equals r squared. Now, if this was a whole lot friendlier, all right, a circle with a center at 0, 0 looks just like this. So if you see a problem where it's just like x squared plus y squared equals 25, you're looking at a nice circle in the middle where if it's equal to 25, square root that, your radius is 5. So you go out 5, draw a nice circle with radius 5, you're done. This is when the center is not 0, 0. But it's not anything to freak out over. It's kind of still a nice picture to draw. What we do is we'll match up the negative 2 with the negative h, which means h, my center, hk, my center is going to be, if negative 2 matches up with negative h, then positive h is going to match up with positive 2. So there you have it. So 2 is going to come from here. If negative k is positive 1, then positive k is negative 1. Now, in this example that I used over here, I said equals 25. If I want to find the radius, if radius squared is 25, square root that. We're not going to worry about positives or negatives. R is going to equal 5, which means my radius is 5. So I have enough information to draw this out. I have more than enough information to draw this out. That's not true. I have enough information to draw this out. My center is 2, -1. Put a dot here. Okay, from somebody who's an idiot at drawing using this pen thing and this tablet thing right here, the best way for me to draw this out is if I know my radius is 5, I'm going to go right 1, 2, 3, 4, 5, put a dot. Go up 1, 2, 3, 4, 5, put a dot. Go left 1, 2, 3, 4, 5, put a dot. Go down 1, 2, 3, 4, 5, put a dot. And then you pray to whatever God you serve that when you draw this out, it's not terrible, which so far I'm okay. Okay is not good, though. Remember, I'm not good at this. This looks bad. No, it doesn't. That actually looks good. And we're almost there. Fine. I'll take it. I'll take it. But that's a circle. Center is 2, -1. Radius is 5. Spin that radius around. Do a better job drawing pictures, and there you have it. Yeah. All right, now we have ourselves something different. It doesn't equal 25 or some large number. It equals 1. We also have fractions. We also have a plus sign. That's 3 forms of happiness that we should have, because what we see here is not a circle. And since this is equal to 1, it's either going to be a hyperbola or an ellipse. But since this is a plus sign, that means it's going to be an ellipse. We have things narrowed down. So I find my formula for an ellipse. But before I write anything out, I need to look for one specific thing. We have fractions here. Underneath both the x and the y, we have a 16 and a 4 respectively. What we need to look for is which denominator is larger. In this case, the denominator underneath the x value is larger. And when that happens, we are using this formula here, x minus h squared over a squared plus y minus k squared over b squared equals 1. Now, when we do this, right, if this were to be flip-flopped around, okay, we need to flip-flop these guys too. And so when we try to find out what our co-vertices are and our vertices, things change. This is going to be one of those things where the major axis is going to be wider. Okay, this is a wider version of an ellipse rather than a taller version of an ellipse. That's why the A and the B matter here, because now we need to figure out what we're dealing with, okay? My center and all that stuff is going to change depending on what we label this. So let's label things. If I were to compare -h to +2, h would be -2. Y is just squared, so like I would pretend that it's y minus 0, so k is 0. That makes life easy. If a squared is 16, a would be 4 because you'd square root 16. And if b squared is 4, then b would be 2 because you'd square root 4. So now I have all this information right here. Okay, the center of this is hk, so my center of my ellipse is going to be -2, 0. My vertices are going to be h plus or minus a k. So my vertices are going to be h, which is -2, plus 4, so that would be 2, k, which is 0, and h, -2, minus a, so -6, 0. My co-vertices, which is where my minor axis is going to be attached to, is going to be h and then k plus or minus b. Okay, h in this case is, where was h? -2. k is 0, k plus 2 is 2, h is negative 2, k minus 2 is negative 2. So let's draw these points out. The center is negative 2, 0. The vertices are 2, 0, and negative 6, 0, so u and u. The co-vertices are negative 2, 2, and negative 2, negative 2. And now we draw it out. So major axis, minor axis, just like I promised it would be. Just like I promised it would be. Let's take a look at this guy right here. Now, you might be looking at that guy right there and saying, that's not a conic section. I don't see parentheses squared. I don't see fractions. I don't see me adding 2 of them. I don't see it equaling 1 or equaling some number. It's equal to 0. This isn't a conic section, you liar. Well, I have news for you, friend. I ain't a liar. This is a conic section. We just have to make it look like one. So this is what we're going to do. Everything is all over the place. This is called general form, where it's blah, 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 blah equals 0, and it's all blah, blah, blah multiplied out. What we're going to do is we're going to take our x values, all 2 of them, and we're going to group them together. 2x squared plus 4x. Then what we're going to do is we're going to take our y values, all 2 of those, and group those together. Minus y squared plus 4y. While we're at it, we're going to subtract 2 from both sides. Minus 2, and now it equals negative 2. That's step 1. Step number 2 into making this looks like a fraction plus or minus a fraction equals 1 is we're going to factor out every number that we can out of each group. So I'm going to factor out a 2. That leaves me with x squared plus 2x. Leave some space. Now, with this one, you might be thinking, I can't factor out anything. That's true, but what I want to do is I want to make sure that my first term is positive. So I'm going to factor out a minus sign. That leaves me with y squared. If I factor a minus out of a positive, it leaves a minus behind. Leave some space. You'll see why. Equals negative 2. Now, what conic sections look like in its standard form is something squared over something. Something squared over something. Well, I don't have that, but this is what I can do. I can use a thing called completing the square to make this a square, and this is how completing the square is done. Take half of the number in front of x, so half of 2 is 1, square that, which is 1, and add that inside the parentheses. Now, be careful. Okay, I just added 1 inside of this parentheses, which also means 1 times 2. I added 2 to the whole left side. If I were to multiply this out, I just added 2 to the left. I can't do that. I can't just add a number to both sides. Well, this is what I can do. You're right. I can't just add 2 to the left unless I add it to the right as well. So if I add 2 to the left and add 2 to the right, everything is balanced. Everything is fair. So if you're like, are you going to do the same thing with the blue guy? I sure am. Take half of 4, which is negative 2. Square that, which is 4, and add that into here. What I just did is I added a negative 4 to the left. And if I add a negative 4 to the left, I have to add it to the right as well. So that's what this leaves us, 2 parentheses. Ooh, that factors out. X plus 1 squared. Oh, minus. Ooh, look, that factors out. Y minus 2 squared. And then this guy becomes negative 4. Now, last time I checked, that's supposed to be regular 1. So why don't I divide everything everything by negative 4. So now what we have is 2 over negative 4, negative x plus 1 squared over 2 plus y minus 2 squared over 4 equals 1. Now you should look at that and say, that's backwards, because it is. So why don't we flip it and write it out normal? Okay, y minus 2 squared over 4 minus x plus 1 squared over 2 equals 1. Now we have a hyperbola, because it's minus, in standard form. Okay, in standard form. So let's graph this. If we have the y first, which we do, we are going to make sure that we set it up like this. We know that the center, and what we're going to do, and why don't I write this all out? Why don't I compare this to the equation for hyperbolas? So this is going to be compared to y minus k squared over a squared. And by the way, if you're wondering, don't we have to figure out which one's bigger? Nope. All we care about is which one are we subtracting from the other. Since this is y blah, blah, blah minus x blah, 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 we're using this formula that's y blah, blah, blah minus x blah, blah, blah. So y minus k squared over a squared minus x minus h squared over b squared equals 1. Okay. Now, having written that out, I can use this color right here. This tells us that k is 2, h is negative 1. It's an h. H is negative 1. A squared is 4. So a is 2. B squared is 2, which means b is root 2, which is like 1.4-ish or something like that, 1.7-ish or something like that. Okay, so that's not going to be fun, but we'll be all right. We'll be okay. All right, now what we need to do is we know this is a hyperbola. Okay, we need to identify our center. So our center is going to be hk, which is negative 1, 2. That's our center. Our vertices are going to be h, k plus or minus a. Okay, so now that I have this, maybe I can erase you because I really need the space. Now that I have everything labeled out. All right, so h is negative 1. K plus a is 2 plus 2, so 4. And the other one will be negative 1. There goes my lights. K minus a is 2 minus 2, which is 0. My covertices are going to be h plus or minus b k. So h, which is negative 1, plus b, so negative 1 plus root 2, and then k, which is 2, or negative 1 minus root 2, 2. All right. Let's draw some points. Center is negative 1, 2. Not that that really matters. My vertices are going to be negative 1, 4. So negative 1, 4, and negative 1, 0. And so this is going to open up downward like that. But how does it stretch out? That's determined by my covertices, which is negative 1 plus pi over 2, so like something like this. 2, so let me move that up. And negative 1 minus pi over 2, so or pi over 2, root 2. So something like that. What I do now is I make myself basically a box. You could use an equation, which I'm not doing for slant asymptotes. Okay. But I'm not going to do that because the equation's not that pleasant. But what this does is this now gives us a guiding point as to where my hyperbola is going to stretch out. Okay, so if I just draw dots like that, draw dots like that, I know that my hyperbola, which I'm going to draw in black, starts at the vertices and then starts following along these dotted lines at some point. Okay, like that. But there you have it. All right, I'm sure that'll happen like 15 times again since I'm in my classroom here in Norristown. That'll happen again several more times before the video's over. NBD, as the kids say. Solve for y, all right? So I'm given what's called an implicit function or an implicitly defined function, which means it's not just y equals. So what I'm going to do is I'm going to get y all by itself. So let's add x squared and add 2 to both sides. Add x squared and add 2 to both sides. Now I have yx minus y equals x squared plus 2. I'm going to factor a y out so that I have just one y living on the left. So y equals x minus 1 equals, y times x minus 1 equals x squared plus 2. And in order to get y all by itself, I'm going to divide everything by x minus 1, divide everything by x minus 1, cross you out. So my equation ends up being y equals x squared plus 2 over x minus 1. Now, what B is asking for is find any asymptotes. Well, knowing from Unit 1, we know that vertical asymptotes exist when the denominator is equal to 0, as long as it doesn't create a hole. Well, 1 would make the denominator equal to 0. So plugging in 1 upstairs doesn't make the upstairs 0, so 1 gives me a vertical asymptote. So I have a vertical asymptote at x equals 1. Great. Now, the other thing that I see is this is a polynomial of degree 2. This is a polynomial of degree 1, which means I'm also going to get slant asymptotes. So the way I figured out what my slant asymptote is I do polynomial division. Whether it's synthetic or long division, it's all good. So I'm going to do x minus 1 is going to divide into x squared plus 0x, because you always have to fill in anything in between, plus 2. And then do polynomial long division. So x times what is x squared? X times x is x squared. Take that x, multiply to this factor here. X squared minus 1x, so just minus x. You subtract the entire row, so subtract the entire row, which means you flip the signs of the entire row. You cross out, drop down x, drop down plus 2. X goes into x one time. I don't care about the rest because the remainder doesn't matter. That is my answer, which means that is my slant asymptote. So my slant asymptote is going to be the linear equation y equals x plus 1. So those are my asymptotes. No horizontal asymptote, because if I have a slant asymptote, that means there's not going to be a horizontal asymptote. You can't have a horizontal asymptote when the degree is higher in the numerator. You just can't have it. You just can't have it. So don't even try. And I think that should do it for conic sections. Part 3 of Unit 4 is about vectors, not the oh yeah guy. Okay, I know what you're thinking, the oh yeah guy from Despicable Me, from Gru and the Minions. No. A vector is basically a line, like so, like this R here, that demonstrates both distance, also called magnitude, and direction. Okay. There's something called vector form, which you can show this vector right here, specifically this vector right here, can be written in vector form like this, 4i plus 3j. What that means is I can demonstrate a vector that is basically, if I were to put a dot here and go right 4, go up 3, and put a dot there, the beginning to the end is going to be my vector in vector form. This is called component form. It demonstrates the same thing, but a faster way of writing a vector. Sometimes most vectors, like vector notation, is like this, so maybe you see it like this with the little arrows. It all depends on the teacher, but that's how I do mine. Okay, and again, these are guys that kind of give you a visual of like, all right, well, I'm drawing an arrow like right 4, up 3, so it's going to look like that. Okay, I am drawing an arrow right 4, up 3, so it's going to look like that. Now from this, we can find the distance. And the way you find the distance is this guy right here. It's basically Pythagorean theorem, which makes sense. If my job is to find that side right there, it's pretty much a hypotenuse. Okay, so if I were to like label you A, label you B, same thing here, label you A, label you B, I can find the distance, which is usually given to you by absolute value markings. The distance equals A squared plus B squared, or 4 squared plus 3 squared. If you're like, could the vectors be negative? Sure, if we're going in negative directions, they can be, but that's not what we have in this example here. That is the magnitude, that gives you the distance. You would get 5 in this case because it's a 3, 4, 5 triangle. The other thing that you can find out is the angle that this vector is heading in. Okay, so very Unit 3 stuff. You do that by doing this stuff you learned in Unit 3. You would take the inverse tangent of the y value over the x value, which in this case would be b over a. So in this case, you're not going to get a pleasant number because this isn't a pleasant number to give, but that's how you would find it. Okay, so vectors, again, gives you magnitude, which is distance. By the way, some books, some teachers, some websites might have it as a double absolute value thing. It's all the same. You can also get the angle by doing the stuff that you learned back in Unit 3. All right, so let's do a few before my lights shut off on me again. So we have something that's written in vector notation. So let me move my face right here. We have something that's written in vector form. So writing this in component form is very easy. If you're like my A and if you're like my B, component form is going to be 4, -4. Just a faster way of writing this stuff out. Graphing this has you start at the unit, okay, or at the origin, go right 4, down 4, put a dot there, put a dot where you began, and that is what my vector is going to look like. Okay, that's me graphing the vector. Finding the magnitude is found by taking the square root of a squared plus b squared. If you're my A and you're my B, or you're my A or you're my B, it would be the square root of +4 squared plus -4 squared. That becomes the square root of 16 plus 16, which is the square root of 32, which is 2 times 2 times 2 times 2 times 2 times 2, 5 of them. So in other words, pull out 2 2s, you're left with a 4, you're left with a 2 on the inside. That's what you're going to get right there. Okay, so that's the magnitude. Okay, so you would write this out as the magnitude of vector v. Now to find the angle, okay, so I'll call that theta, you're going to do the inverse tangent of b over a. So in this case, the inverse tangent of -4 over +4, which simplifies to the inverse tangent of -1. Now, the inverse tangent of -1 could be one of two options, but we know which option that we want. If you were to like throw this in a calculator and the calculator would say something to the effect of, what would that be, 3 pi over 4? It's not the guy we want. The guy that we want is 7 pi over 4. It's 7 pi over 4 because we exist and live in quadrant 4 because that's the direction that we're going. So the angle is going to be 7 pi over 4. Okay? Some vector fun for you. You could say, oh yeah, now. I'll pause. All right, moving my head again. I'm giving you two vectors, A and B. and I'm going to ask you to find the dot product of A and B, and then the unit vector, and then do a little bit of algebra. So the dot product, okay, what you do with the dot product is you take both of your vectors, okay, that are in vector or component form. Thank goodness for that. If it's not in component form, put in component form. You're going to do, so this is going to be 5, 7, -2, 1. The way you find the dot product is you take the first two numbers, or the first number in each vector, multiply them. So 5 times -2. You are going to add the product of the second two numbers. So those of you who are like, I love matrices, this kind of reminds me of that, you're kind of on the right path, kind of. By the way, we'll get to matrices in a little bit. But what this is this is going to be -10 plus 7, so the dot product is -3. Find the unit vector of B. Now, the unit vector is basically 1. So what do I do to B to get back to 1? Well, this is what you do. The unit vector is found. And by the way, unit vector is usually given to you by that little hat-looking thing. What you do is you take the vector that we're dealing with. So the unit vector of B, let me make it B, okay, is going to be regular B over the magnitude of B. So why don't I quick find the magnitude of B? B is going to be -2 squared plus 1 squared, which is going to be 4 plus 1, which is going to be the square root of 5. So B is -2, 1 divided by √5, which makes this -2 over √5, 1 over √5. And if you wanted to really be specific, multiply the top and the bottom by √5. That gets you -2 √5 over 5. Multiply the top and the bottom by √5. So √5 over 5. Because, you know, it's against the law to have square roots in the denominator. Against the law. This is just regular vector algebra. When stuff's given to you in component form, it's exactly the way it looks. 3 times vector A is going to be 3 times vector 5, 7, minus 5 times vector B is going to be -5 times -2, 1. That's 15. 21 plus 10, -5. And then you just add the components in the forms that they're in. So 15 and 10 is 25. 21 minus 5 is 16. So A, when drawn out, gives you something that looks like this, but much longer. B, when drawn out, gives you something that looks like this. So basically what they're saying is if you took 3 of these guys, boom, 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 where you can't see, and then subtract, which means go more in that direction, 5 of those guys, where are you going to end up? You're going to end up at 25, 16 away from the origin. So now you know. Now you know why you did what you did. I believe that's it for vectors. Yeah. This is the last part about Unit 4, and it's matrices. Okay, matrices. I love matrices. They're fun for me. I don't know what's wrong with me, but I enjoy them. Now, matrices, basically, you just have these little brackets, and they contain numbers called elements. You separate or you determine what a matrix is by the number of rows it has and the number of columns it has. Always go rows by columns. So if I wanted to take a look at this guy, I would be like, you have 2 rows and you have 3 columns. You have 2 rows and you have 2 columns. You have 3 rows and 1 column, so on and so forth. You can only add or subtract matrices that have the exact same dimensions. You can only multiply matrices if this happens. So for example, if I called you A and I called you B, if I wanted to multiply A times B, the only way that you can multiply A times B is you write out the dimensions of A, you write out the dimensions of B, and if the two numbers on the inside match, you can multiply them. In this case, they don't. So if I were to ask you, do A times B, your answer would be, well, you can't. It's an undefined matrix. Can't do it. Now, if I were to ask you to do B times A, which is 2 times 2, and then 2 times 3, you can do it because these numbers do match. And the resultant matrix will be a 2 by 3 matrix. So that's what we're going to mainly focus on is matrix multiplication with these because matrix addition and matrix subtraction is pretty easy. And we'll kind of do that anyway as we do a couple of these problems that we're about to do. All right, so here's 3 matrices. I'm going to ask you to do, and by you, I mean I'm going to do it. I'm going to have us do B times A. So here's B, here's A. Let me write it out. -2, 9, 4, -6, 8, 0, times A, which is 3, -7, -1, 5. Now, before we go any further, we need to make sure we can do this. This is a 1, 2, 3 rows, 2 columns. This is a 2 rows, 2 columns. We can do it, and we're going to end up with a 3 by 2 when we're done. Okay, so that's 3 rows. Get a different color. 3 rows, 2 columns. So now the way you multiply matrices together is you take the first matrix, you split it up by rows. You take the second matrix and split it up by columns. I'm going to begin, oh wow, that looks like my stomach. I'm going to begin with the first row, because of the abs. I'm going to multiply the first row to the first column to get the first row, first column. What you do is you take the first element in each one, so -2 and -3, and multiply them. So -2 times +3. I'm sorry if I said -3. I think I did. -2 times +3. Then you plus 9 times -1, the second element in each. Okay, so first row, first column, multiply the first elements plus multiply the second elements. Second column, first row now. So first row, second column, you're going to repeat the process. -2 times -7, the first elements in each part. -2 times -7 plus 9 times 5. Then you repeat. Second row, first column, 4 times 3 plus -6 times -1. Second row, second column, 4 times -7 plus -6 times 5. Okay. Third row, first column, 8 times 3 plus 0 times -1. Third row, second column, 8 times -7 plus 0 times 5. Now it's just PEMDAS a bunch of times. Okay, so let's write these out a little bit more. -6 minus 9, 14 plus 45, 12 plus 6, -28 minus 30, 24 plus 0, -48 plus 0. And then our final answer, our resultant matrix, negative 15, 59, 18, negative 58, 24, negative 48. And that's how it's done. Isn't that neat? It is neat. All right, we're using the same matrices, and this time we're going to find AC. So here is A, again, 3, negative 7, negative 1, positive 5. C is 4, 1, 8, negative 3, 6, negative 2, 7, 5. Okay. You have 2 rows, 2 columns. You have 2 rows, 4 columns. These guys combine, and we'll end up with a 2 by 4. Gross. All right. No big deal, though. I can handle this. So what did I say? 2 by 4, so that's 2 rows, 4 columns. I won't show quite as much work as I did in the last one. I'll do this a little bit faster because honestly, I don't even have the space for it, but that's all right. Take your first matrix, split it up by rows. Take your second matrix, split it up by columns. Okay? First row, first column. First row, first column. 3 times 4 plus negative 7 times 6, which is minus 42. Okay? First row, second column. 3 times 1. Negative 7 times negative 2 is plus 14. First row, third column, 3 times 8, which is 24. Negative 7 times negative 7 is negative 49. First row, last column, 3 times negative 3 is negative 9. Negative 7 times negative 5 is negative 35. Okay, second row, first column, negative 1 times 4 is negative 4, plus 5 times 6 is 30. Second row, second column, negative 1 times 1 is negative 1. 5 times negative 2 is negative 10, so plus negative 10. Second row, third column, negative 1 times 8 is negative 8, plus 5 times 7, which is 35 again. And then negative 1 times negative 3 is 3, plus 5 times 5 is 25. 12 minus 42 is negative 30. 3 plus 14 is 17. 24 minus 49 is negative 25. Negative 9 minus 35 is negative 44. Negative 4 plus 30 is 26. Negative 1 minus 10 is negative 11. Negative 8 plus 35 is 27. And 3 plus 25 is 28. Let's do a few more. Let's do a few more. How about CB? C, I'm not even going to write it out. C is a 4 by 2. No, it's not. It's a 2 by 4. Boy, would that change things. B is a 1, 2, 3, 1, 2. I tricked you. I tricked you. This one's undefined. Can't do it. Can't do it. Now let's solve some equations. Just kidding. Let's find the determinant and the inverse of a 2 by 2. You can find determinants and inverses of non-2 by 2s, but they're a god-awful nightmare, and you're not going to need to know that for AP Precalculus. The determinant. Now, what the determinant of a matrix does is it lets you know whether or not you can do an inverse. Okay. In matrices, you don't have what's called, you don't divide matrices. You can't do that. So what you're going to use instead is an inverse. And there are times where you can't do the inverse and you use the determinant to make that determination. Now, I'm going to view A from the viewpoint of it being A, B, C, D. All right. So A is a 2 by 2. I'm going to match that up with A, B, C, D. The determinant of any matrix is found by doing AD minus BC. So A here, if you're A, if you're B, if you're C, if you're D, I would end up doing 3 times 5 minus negative 7 times negative 1. You become 15, you become 7, you become 8. Now, you can't, by the way, you can get a determinant. If it asks you to get it, find the determinant, you can get anything. Now, there becomes a problem if the determinant is 0. If the determinant is 0, you can't take the inverse. Why? Well, the way you find the inverse is you do 1 divided by the determinant. So if the determinant was 0, I'd be asking you to do 1 divided by 0, which you can't do. You take that fraction, you multiply it to this matrix where you swap the D and the A, and you make the B and C the negative versions of itself, or the opposite versions of itself. So what this is going to look like is 1 over 8 times the 2 by 2 matrix where I swap the 5 and the 3, and I make 7 positive, and I make 1 positive. So this is what's called scalar multiplication for matrices. You literally just distribute that 1 over 8 to every element inside the matrix. 5 over 8, 7 over 8, 1 over 8, 3 over 8. That is the inverse. Okay? And again, you can't divide matrices, so the inverse is going to help us for when we see problems that look like this. Okay, this problem is a standard solving the matrix problem. Now, in AP Precalculus, it might be written out in a strange way where it would say something like, vector. It might be written out as a vector. It's just really weird the way AP Precalculus words them sometimes. In fact, maybe what I'll do is while I'm talking right now, I'll put up on the screen an example of the way it's worded, or a way a problem like it is worded. And so what you're just going to have to understand is, we take a problem that looks like this, and we're going to turn it into a problem that looks like what the guy here is showing us. Okay, so what this is saying is C is a matrix, and I'm doing a matrix times C minus a matrix equals a matrix. So I have to get C all by itself. And if you're looking at this and thinking, this kind of reminds me of something like if I had a problem like this in class and I was asked to do a problem like this in class, don't I just subtract 10 and divide 3? Yes. And we're going to follow the same rules except for the divide 3 part, which we'll get to. So what we're going to do to start this problem out is we're going to subtract this matrix from both sides. Now, matrix subtraction is allowed as long as the dimensions for each matrix are exactly the same, which they are here. Okay. So this will cancel out. So minus 4, negative 9, negative 5, negative 2, 0, 9. Now, I struggle with my ADHD brain sometimes with these. So instead of saying, because what I'm going to do is 12 minus 4, negative 2 minus negative 9, I screw these up from time to time. So what I'm going to do is I'm going to make this plus and flip the signs and everything here. Is it necessary? No. Is it helpful for me? Yeah. All right, so 12 minus 4 is 6. Negative 12 plus 9 is negative 3. Negative 15 plus 5 is negative 10. 7 plus 2 is 9. Negative 12 and nothing is negative 24, not 12. 4 plus negative 9 is negative 5. So now I have a matrix, 2 by 2, times C equals that. Now, when you're solving matrix equations, there is a rule that says this. Say you have A times C, where C is what you're solving for, equals B. That's what I have. You're basically my A, you're basically my B, and C is the matrix that I'm going to get. You're not allowed to divide A. That's like the 15th time I've said that. You can't divide a matrix. But what you do instead is you take the inverse on the left side of both sides. And what that does is that cancels that out. And now I get C equals whatever the product of inverse A and B are. So what I need to do is I need to take this to the side and find the inverse of A. Now, how do I find the inverse? I just did it. It's 1 over the determinant, which is AD minus BC. And then you multiply that to, let's flop these or swap these. Let's make U positive and let's make U negative. Okay, so 1 over AD, which is 2, minus negative 3. So 2 minus negative 3 is 5. Ugh. This is not going to be fun, and this is not going to be pleasant whatsoever. Did I do that right? 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 Unfortunately, I did. So AD, again, is 1 times 2 minus negative 1 times 3, so 1 over 5 times 2, 1, negative 3, 1 is going to give us 2/5, 1/5, negative 3/5, 1/5. Ugh. So using this rule, C is going to equal the A inverse of B. So C, which is what I'm solving for, is going to equal the A inverse, which is 2/5, 1/5, negative 3/5, 1/5, times B, which is 6, negative 3, negative 10, 9, negative 24, negative 5. This problem's going to take a few minutes, which means my light's probably going to turn out on me again. Separate U by rows, separate U by columns. This is a 2 by 2 that we're multiplying to a 2 by 3, which means we're going to get a 2 by 3. All right. 2/5 times 6 is 12/5. Plus 1/5 times 9 is 9/5. Okay, I'm going to have to, let me separate these, okay. 2/5 times negative 3 is negative 6/5. 1/5 times negative 24 is negative 24/5. Oh, this will be nice. 2/5 times negative 10 is negative 4. I don't know why that took me so long. And 1/5 times negative 5 is minus 1. Oh, how lovely. Now back to it being terrible again. Negative 3/5 times 6 is negative 18/5 plus 9 over 5. We're working from 9 to 5. Negative 3/5 times negative 3 is positive 9/5 plus negative 24 over 5, so minus 24 over 5. And it gets nice again. Negative 3/5 times negative 10 is positive 6. 1/5 of negative 5 is minus 1. All right, so let me get rid of U, just in case things simplify. Okay, just in case things simplify, I'm going to leave my space down here. So we have 21 over 5, 9 plus 10 over 5. Negative 30 over 5, so I'll deal with that in a second. Negative 5. Negative 9 over 5. Negative 15 over 5, so I'll deal with that in a second. And 5. So last but not least, I have 21 over 5, negative 6, negative 5, negative 9 over 5, negative 3, and 5. And my light did not turn off on me. Yes! Little battles, little victories. Use matrices to solve a system of equations. I can take any two-variable system and solve it. I could take any system and solve it using matrices, but it's nice when things are lined up perfectly as if this is an elimination problem, and I could just go and use matrices. It might even be easier, maybe, debatable. Maybe if you have a calculator, it would be easier. I don't know. But x, y equals a number. Everything's in order the way it should be. If it wasn't in this order, put it in this order. What you're going to do is you're going to take the coefficients of the top and the bottom equation and make that a 2 by 2 matrix. So negative 3 and negative 4, 3 and negative 5. Okay. I'm going to make another matrix that involves the x and the y, like that. And it's going to equal a 2 by 1 that involves what the constants are over here. Now, again, this is very similar to the problem that we just did, which seems like months ago, where if I give you something in the form ax equals b, I know the last time I used c, but that's because I had the letter c. If I want to get x all by itself, and this would be my x, I would inverse on the left side of both sides, which crosses u out, and so x is going to equal the a inverse of b. So if I called you A and if I called you X and I called you B, I could just do that guy right there. So I need to find the A inverse. So let's do that down here, over here, or something like that. Let's find the A inverse. I don't know why that bumped out. The A inverse is going to be found by doing 1 over AD minus BC. So negative 3 times negative 5, which is 15. Minus BC, which is minus negative 12. And you're going to multiply it to the matrix where you swap these two. So negative 5 and negative 3 are swapped. You're going to flip the signs of these two. So positive 4 and negative 3. And you get, oh, no way, 1 over 27? I immediately regret this problem. Oh well. Negative 5, 4, negative 3, negative 3. Okay, which becomes negative 5 over 27, 4 over 27, negative 1 over 9, negative 1 over 9. All right. So is this easier? No. Is this another option? Yes. XY is going to equal A inverse, which is negative 5 over 27, 4 over 27, negative 1 over 9, negative 1 over 9, times 20 and 25. So this is a 2 by 2 times a 2 by 1, which means we'll get a 2 by 1. That's not bad. That's not so bad. Okay, split u. You're already split. Negative 5 times 20 is negative 100 over 27 plus, no way, 100 over 27. Oh, look at God. Negative 1 over 9 times 20, so 20 over 9 minus 25 over 9. So the top part is 0. Is that minus? This is negative. Oh, that was a close one. Negative 20 minus 25 is negative 45 over 9. So what this is telling us is that x, y equals 0, negative 5. I don't know why I put that line there. 0 over negative 5. Let's get rid of that line. Negative 5, negative 5, negative 5, negative 5. So x is equal to 0. So my final answer is going to be this point right here, 0, negative 5. So if I tested that, negative 3 times 0 is 0. Negative 4 times negative 5 is 20. Praise the Lord. 3 times 0 is 0. Negative 5 times negative 5 is 25. It worked. Was it easier? No, not in any way whatsoever. But we did it. Okay, we did it. Which leads me to this problem, which is very, 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 very similar to what we saw before. Now, this is a calculator problem, and yes, I will eventually use a calculator, but not quite yet. This is very similar to what we saw before, okay, where you have a random matrix floating around, a matrix times a matrix equals something. So what I'm going to do, because the numbers are not that bad, is I'm going to subtract this matrix from both sides. Now, this is a 3 by 3, and I'm going to subtract this by a 3 by 3 over there. So that will cross out. So I'm subtracting this matrix, which is 0, negative 4, 8, 1, negative 1, negative 3, 4, negative 5, negative 2. Someone's calling me from Harrisburg. It might be the governor, but it's too late. Hung up. I don't like minusing, so I'm going to plus the opposite. So plus the negative, opposite, 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 opposite. And so now what we have is we have 2, 2, 1, negative 5, negative 8, 2, 1, 3, negative 1, x equals 1, was that plus 4? So negative 18, 5, 32, 24, 16, negative 12, negative 27, negative 9. Now we're going to use that rule that we've used twice already. And we're going to call you A. And we're going to call you B. And if AX equals B, we could do the A inverse of both sides and get X equals inverse AB. And that's what I'm going to do. I'm going to run to my calculator. And I'm going to type that into A. I'm going to type that in for B and find out what A inverse B is, because I do not want to find the inverse of A. So let's go to the side and do that. Let's have some fun with matrices, shall we? What I have is, as you can see on the screen, I need to find A inverse B. So what I'm going to do is I'm going to set up A and I'm going to set up B and do that. So you click second, the matrix guy, and then you edit A. So we will actually edit A. It's a 3 by 3. So you hit enter on all of those guys and you just type it in. 2, 2, 1, negative 5, and make sure it's negative 5, not minus 5 like I accidentally just did. Enter. Negative 8. Enter. Then you have 2, 1, 3, and then negative 1. Okay, so scan through it. Make sure you didn't make any mistakes. I did it, so let's quit. Now I'm going to edit B. So second matrix, go to edit, and we're going to edit B. Okay, that one is also a 3 by 3. And we're going to start typing away. 1, negative 18, 5, 32, 24, 16. Listen to me announcing numbers. Negative 12, negative 27, negative 9. Okay, scan through it. I don't see any mistakes on my end, so let's quit to our home screen. Now what I need to do is I need to do the A inverse of B. So you hit second, matrix, and hit A to load A up on the home screen. The inverse button is the same button as the matrix. How about that? Then you do second, matrix, and now we're going to do B. And so we're going to multiply these guys together, and good Lord. Although they're not the worst in the world, they're definitely not pleasant. I wonder if by hitting math frac, it'll put them in fractions for me. Let's find out. Let's find out. Let's find out. Yes. So there you go. You learned 2 things today. That's how I'm going to write it out. So let's write it out. All right. Not too good, but not too bad either. So x is going to equal negative 2, 80 over 3, regular 2, negative 1, negative 25, negative 2 again, 7, negative 64 over 3 and 5. Great. 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 All right, last problem and yet another calculator one, although I'm not sure we're going to need it, but we'll see. 2 streaming services, FlixNow and StreamSavvy, have just launched in a new residential area. Initially, they have half of the market for the streaming for streamed movies. I can't read. A subscriber who streams from FlixNow has a 60% chance probability of streaming from FlixNow the next time and a 40% chance of streaming from StreamSavvy. On the other hand, a subscriber initially streaming from StreamSavvy has only a 30% chance likelihood of streaming from StreamSavvy the next time and 70% of streaming from FlixNow. Look at you, FlixNow. What is the probability of a customer streaming from each service a third time? All right, so since there's a 50% market, okay, the initial probability vector is 50-50. Okay, so that is going to be 0.5, 0.5. Okay, that's the initial probability vector. Okay, now the transition matrix is going to come from, it's going to look like this, and I'm going to label them a little bit better. Okay, what do we have? FlixNow, so FN, and then we have StreamSavvy, and then we have FlixNow, and then we have StreamSavvy. Okay, so a subscriber who streams from FlixNow has a 60% probability of streaming from FlixNow the next time. So 60% means you're going to be 0.6 when these guys line up, which makes you 0.4. Okay. Because it all is supposed to left to right adds up to 1. On the other hand, a subscriber initially streaming from StreamSavvy has only a 30% chance likelihood of streaming from StreamSavvy the next time. So that is going to put you at a 0.3 here, which makes you at a 0.7. All right, so what I need to do, let's get these out of the way, although I really don't need to, but let's just get them out of the way. That's my transition matrix right there. I need to multiply these guys together. So I don't really need, let's see if I need it. Let's see if I need it. And let's write this out. Okay. And again, maybe I need to relabel things again. In fact, I will. Your FN, which I'm not supposed to say, your StreamSavvy, FN, SS, what were you? FN, that's a N, SS. Let's multiply these guys together. Okay, so you are a 1 by 2, you are a 2 by 2, which means at the end of the day, I'm going to end up with a 1 by 2. Okay, which will look like this. Split it down the middle. Now remember, 0.5 means half, so let's not go crazy with the fractions here. First row, first column, half of 0.6 is 0.3 plus half of 0.7 is 0.35. Okay. First column, or I'm sorry, first row, second column, half of 0.4 is 0.2, and half of 0.3 is 0.15. So you're going to end up being 0.65, and you're going to end up being 0.35. Okay. The question is what is the probability of a customer streaming from each service for a third time? Okay. So what this guy gives us is this is, okay, the Fn, and this guy is the SS. So the third time is flicks now, because that's what the Fn stands for. Flicks now is going to have a 65% chance of somebody streaming a third time, whereas stream savvy is going to be 35% chance. Okay. And that actually does it. I know it says I have one more. I know I don't. I don't. So that's Unit 4. Again, Unit 4 is not tested on the AP exam, but you might have a teacher that goes through it. I don't know how long this video is going to be, like an hour and a half, 2 hours long. But, you know, we covered quite a bit in a very short period of time. So, you know, this will give you a good, like, review if you're taking, like, a test on Unit 4. It won't give you 100% because we don't cover everything super in depth, but we cover everything slightly. So at the very least, if you're taking like AP Calculus, maybe watch this and this will help bring stuff back. Of course, I'm telling you this at the end of the video, which if you're watching it, you made it this far, thank you, and I appreciate you. But that'll do it for Unit 4. Thank you guys. Thanks for watching. Have a wonderful day. Bye.